Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Scanning Tunneling Microscope STM from the paper Physics at Nanoscale. So the learning objectives of this module are: first, we will be discussing the history of STM. Next, the converse piezoelectricity effect will be discussed. Then we will discuss the different scanning modes of STM. Then we will discuss the schematic of STM. After this, we will discuss the theory of STM, that is to determine the expression for tunneling current. Then we will discuss the scanning tunneling spectroscopy. Lastly, we will discuss how the atomic manipulation is done with STM. So students, let us start with a basic introduction about the module. The scanning tunneling microscope STM is widely used in both industrial and fundamental research to obtain atomic scale images of metal surfaces. It provides a three-dimensional profile of the surface, which is very useful for characterizing the surface roughness, observing surface defects, and determining the size and the conformation of molecules and aggregates on the surface. So, we have the various objectives or the various points related to STM. That is, it has the atomic resolution several orders of magnitude better than the best electron microscope. Quantum mechanical tunnel effect of electron is there. In situ capable of localized, non-destructive measurements or modifications is possible with STM. It is used in material science, physics, semiconductor science, metallurgy, electrochemistry, and molecular biology. Scanning probe microscopes SPM. They are designed based on scanning technology of STM. So let us discuss the history of scanning tunneling microscope. The scanning tunneling microscope was developed at IBM Zurich in 1981 by Gerd Binning and Heinrich Rohrer, who shared the Nobel Prize for Physics in 1986 because of the microscope. So here a probe tip, which is usually made of tungsten or platinum iridium alloy, is attached to a piezo drive, which consists of three mutually perpendicular piezoelectric transducers, X piezo, Y piezo, and Z piezo. So upon applying a voltage, a piezoelectric transducer expands or contracts. So by applying a sawtooth voltage on the X piezo and a voltage ramp on the Y piezo, the tip scans on the XY plane. So using the coarse positioner and the Z piezo, the tip and the sample, they are brought to within a fraction of a nanometer with each other. So the electron wave functions in the tip overlap the electron wave functions in the sample surface. So a finite tunneling conductance is generated, and by applying a bias voltage between the tip and the sample, a tunneling current is generated. Now students, let us discuss about the STM. That is, STM is an electron microscope that uses a single atom tip to attain the atomic resolution. So it consists of a piezoelectric scanner. Now, as shown in the figure above, which consists of the various components of STM, the components of STM includes the scanning tip, piezoelectric controlled height, and XY scanner, coarse sample to tip control, vibration isolation system, and computer. So the resolution of an image is limited by the radius of curvature of the scanning tip of STM. So additionally, image artifacts can occur if the tip has two tips at the end rather than a single atom. This leads to double tip imaging, a situation in which both the tips contribute to the tunneling. Therefore, it has been essential to develop processes for consistently obtaining the sharp, usable tips. Recently, carbon nanotubes have been used in this instance. Now the tip is often made of tungsten or platinum iridium, though gold is also used. Tungsten tips are usually made by electrochemical etching and platinum iridium tips by mechanical shearing. So due to the extreme sensitivity of tunnel current to height, proper vibration, insulation, or an extremely rigid STM body is imperative for obtaining the usable results. In the first STM, by Binning and Rohrer, magnetic levitation was used to keep the STM free from vibrations. Now mechanical spring or gas spring systems are often used. Additionally, mechanisms for reducing eddy current are sometimes implemented. So maintaining the tip position with respect to the sample, scanning the sample and acquiring the data is computer controlled. So computer may also be used for enhancing the image with the help of image processing as well as performing the quantitative measurements. Overview of STM. An extremely fine conducting probe is held at about an atom's diameter from the sample. So electrons, they tunnel between the surface and the tip, producing an electrical signal. While it slowly scans over the surface, the tip is raised and lowered in order to keep the signal constant and maintain the distance. So this enables it to follow even the smallest details of the surface it is scanning. So let us now discuss the tip, which is a crucial part of STM microscope. As we will see later, it is very important that the tip of the probe be a single atom. So tungsten is commonly used because you can use the electrochemical etching techniques to create very sharp tips like the one above. So STM tips should be conducting. Metals like platinum. STM plays with the very top outermost atom at the tip as shown in this figure and the nearest atom on the sample. So the whole tip is not necessarily very sharp in shape, different from the case of AFM where spatial contact is necessary and crucial for feedback. So the question arises, how do we obtain these wonderful tunneling tips where only one atom is at the top? The answer to this is that it is really easy to obtain such tips simply by cutting a thin metal wire using a wire cutter. There is always a single atom left over at the every tip. So students, let us now discuss about the quantum tunneling. STM is based on the concept of quantum tunneling. So when a conducting tip is brought very near to the surface to be examined, a bias or voltage difference applied between the two can allow the electrons to tunnel through the vacuum between them. So the resulting tunneling current is a function of tip position, applied voltage, and the local density of states, LDOS, of the sample. So information is acquired by monitoring the current as tips positions scans across the surface, and it is usually displayed in the image form. So STM can be a challenging technique as it requires extremely clean and stable surfaces, sharp tips, excellent vibration control, and sophisticated electronics. But nonetheless, many hobbyists have built their own. So the second tip here shown above is recessed by 2 atoms and thus carries about 1,000,000 times less current. That is why we want such a fine tip. If we can get a single atom at the tip, the vast majority of the current will run through it and thus it gives us the atomic resolution. So the important note over here is that the STM does not measure the nuclear position directly. Second, rather it measures the electron density clouds on the surface of the sample. Next, in some cases, the electron clouds represents the atom locations pretty well, but not always. So let us now discuss quantum tunneling. Through a barrier, quantum mechanics predicts that the wave function dies off exponentially. So psi d equal to psi naught multiplied by exponential minus kd, where k is equal to root of 2m multiplied by phi minus e divided by h cut. So the probability of finding an electron after a barrier of width d is wd equal to modulus of psi d the whole square equal to the modulus of psi naught the whole square multiplied by exponential minus 2kd, and I is equal to Fv multiplied by exponential minus 2kd, where Fv is the Fermi function which contains a weighted joint local density of states. This is a material property obtained by measurements. So I is proportional to exponential minus 2kd, where k is approximately equal to root of 2m phi by h cut. So plugging in the typical values for m, d and phi, where phi is the average work function of the tip. When d changes by 1 angstrom, the current changes by a factor of about 10. So let us now discuss about the converse piezoelectricity. Piezoelectricity is the ability of certain crystals to produce a voltage when subjected to mechanical stress. So when you apply an electric field to a piezoelectric crystal, the crystal distorts as shown in the figure. This is known as converse piezoelectricity. The distortions of a piezo is usually of the order of micrometers, which is in the scale needed to keep the tip of the STM a couple angstroms from the surface. So let us now discuss the two scanning modes of scanning tunneling microscope. First, on the left hand side, it is the STM constant height mode, and on the right hand side, this shows the STM constant current mode. So students, as we have already discussed about the quantum tunneling, let us more elaborately discuss this tunneling effect. As we can see over here that classically there is no tunneling possible if the energy of a particle is less than the potential barrier V0. But quantum mechanically it is possible as shown in the figure on the right hand side, and the tunneling current IT is proportional to V by D multiplied by exponential minus A phi by 2 multiplied by D, where A is equal to 1.025 eV to the power minus 1 by 2 angstrom minus 1, and IT equal to 10 picoampere, approximately 10 nanoamperes, and V is 1 millivolt to 3 volts. So now D decreases by 1 angstrom, then IT will be reduced by 10 times as shown in the graph on the left hand side. So these are the STM images of silicon 111, where as you can see this shows the empty state image, and the figure on the right hand side shows the filled state image. The below figure shows the STM images of germanium 111. So this shows the atomic structure of platinum 001 surface, which was published in Surface Science, and this is being recorded by scanning tunneling microscope. So students, these are the images showing the in-plane structure of gold 111 surface with a 22 multiplied by root 3 reconstruction. Now here the circles and the crosses correspond to the atoms in the first and the second surface layers respectively. And here surface atoms in both sides of the figure lie on the FCC sides, whereas atoms in the center of the figure lies on HCP sides. The domain walls dislocation lines involves the atoms in bridge sites. So, the large scale image of gold 111, that is 22 multiplied by root 3 reconstruction. Now here the gold 111 surface reconstructs at room temperature to form a 22 multiplied by root 3 structure, which has a twofold symmetry. So on a large scale, 3 equivalent orientations for this reconstruction coexist on the surface. Furthermore, on an intermediate scale, a herringbone pattern is formed. So let us now discuss the basic theory behind STM. Consider a one-dimensional tunneling problem as shown in this figure, where the tunneling current EV is very much less than phi, and so the current I is proportional to V by S multiplied by exponential of minus A phi to the power 1 by 2 multiplied by S. And A is equal to 1.025 EV to the power minus half Armstrong to the power minus 1. So the tunneling current, the expression for the tunneling current can be written as I T to S equal to 2 pi E by H cut multiplied by summation over mu nu over F as a function of E mu multiplied by 1 minus F as a function of E nu plus EV multiplied by m mu nu modulus the whole square multiplied by delta as a function of E mu minus E nu minus EV, where Fe is the Fermi function, E mu is the energy of state mu, where mu and nu run over all the states of the tip and the surface respectively. Mu nu is the tunneling matrix element, which is given by m mu nu equal to h cut square by 2m multiplied by integral over ds vector multiplied by psi mu star grad of psi nu minus psi nu grad of psi mu star, where psi mu is the wave function and the integral is over any plane in the barrier region. So the current I will be equal to I T to S minus I S to T equal to A prime multiplied by minus infinity to infinity rho T as a function of E multiplied by rho S E plus EV multiplied by modulus of NE the whole square multiplied by Fe minus Fe plus EV dE, where rho S and rho I are the densities of states in the sample and the tip respectively. Now the tunneling current will be equal to I is equal to A prime multiplied by minus infinity to infinity, the integral over rho t E multiplied by rho s E plus EV multiplied by the modulus of ME the whole square multiplied by FE minus FE plus EV dE. And the transmission probability of the electron is given by ME equal to exponential of minus A phi to the power 1 by 2 multiplied by S. So usually we assume rho t is featureless, that is rho t is approximately constant, and the sample electronic states dominates the tunnel spectra. As you can see in this figure that however the tip might have effect on the tunnel spectra if number 1 we have automatically sharp tips, or second the tip has picked up a foreign atom. So let us take a case for metals. In the low voltage limit, I is proportional to V multiplied by rho s as a function of RT EF multiplied by rho t as a function of EF, where rho s RT EF is the surface density of states of the sample at the center of the tip RT. So rho s as a function of RE equal to summation over nu over the modulus of psi nu as a function of R the whole square multiplied by delta E nu minus E. Now here rho t as a function of EF is the density of states of the tip at the Fermi level and is often regarded as a constant. Tunneling microscopy. So scanning tunneling microscope provides the atomic scale topographic information and atomic scale electronic information. However, the mixture of geometric and electronic structure information often complicates the interpretation of observed feature. Now there are several spectroscopic modes. First is voltage dependent STM imaging. Second, tunneling IV curves, current imaging tunneling spectroscopy CITS. Third is scanning tunneling spectroscopy STS, which shows the variation of dI by dV as shown in this figure, and a topograph. So these are the STM images of single-walled carbon nanotubes. Electronic structure of single-wall nanotubes, that is, the first is armchair nanotube NM, which is metallic. Second is a zigzag nanotube N0, which can be metallic when N equal to 3Q, and otherwise it is semiconducting. Third is a chiral nanotubes NM, which is metallic when M equal to N plus 3Q. Uses of STM. First, it is used in measuring high precision optical components and disk drive surface roughness of machined or ground surfaces. Secondly, below is a trace of an individual turn mark on a diamond turned aluminium substrate to be used for subsequent magnetic film deposition for a high capacity hard disk drive. So by measuring the variations in current, voltage, tip surface separation and their derivatives, the electronic properties of different materials can be studied. One such element studied was the buckyball C60. When you press down on a buckyball by 1/10th nanometer, it lowers the resistance of the buckyball by 100 times. Now there are different STM ideas. So students, you could not decide not to use piezoelectricity to keep the distance between the tip and the surface equal at all the times, and instead use the current measurements to determine the surface of a sample. So the pros or the advantages of STM is that you can scan much faster, but the cons or the disadvantages are the surface must not have cavities more than few angstroms deep, that is an atom or two, because of tunneling. So students, let us summarize what we have learnt in this module. First, we discussed the history of STM. Secondly, the converse piezoelectric effect on which this STM is based on was discussed. Thirdly, the different scanning modes of STM were discussed. Next, we discussed about the schematic of scanning tunneling microscope. Then we discussed the theory of STM, where we found out the expression for tunneling current. Then we discussed the scanning tunneling spectroscopy obtained from STM. Lastly, the atomic manipulation which can be done with STM was discussed. Thank you.